All right. Well, it is my pleasure to introduce this afternoon's afternoon session post lunch speaker, someone who's become a good friend of mine, Jeff Sutton, Dr. Jeff Sutton, stranger to nobody here certainly. I'm still obligated to read off some of the things about him, though. As you all know, Jeff is the Friedkin Chair for Research in Sensory System Integration and Space Medicine. Usually I don't read off of notes, but that was so long I couldn't remember it. At the Baylor College of Medicine, and he's, of course, a professor there, full professor, and the founding director of the Center for Space Medicine, of which I'm still a small part of, as are many of the folks here. Dr. Sutton is also chairman, of course, TRISH, the Translational Research Institute for Space Health, and previously, of course, for many, many years, he was the CEO and director of the National Space Biomedical Research Institute. And of course, I worked for Jeff for a number of years, and as I said, really enjoyed getting to know him and becoming a good friend. So please help me in welcoming Jeff to the podium.
Well, thanks a lot, Igor. I mean, you don't need to applaud or anything. So this is a short but very important panel on space radiation. And as folks know, there are really two sources of space radiation. I mean, one from the sun, which are protons traveling at near relativistic speeds, and then the other source being from outside our solar system, galactic cosmic rays, which also consist of protons, but also heavy ions up to iron. And the Van Allen belts, of course, protect us here on Earth from SBEs and GCR effects, but beyond low Earth orbit, radiation poses a significant hazard for astronauts. And there have been recent advances in characterizing the nature of space radiation, but there's still a lot of open questions. On Earth here, facilities such as NSRL in the US and ESTEC in Europe have increased capabilities to study tissues and animals with a mix of protons and heavy ions. And this is very interesting work, and the studies using these and more sophisticated beams are shedding new light. So it's hard to do the topic justice in this 1 hour panel, but we're fortunate to have excellent panelists spanning expertise in solar physics and radiation biology, space physiology, countermeasures, and other related areas. So the plan is to go down the line and to ask each panelist to briefly introduce himself or herself, and then give some perspectives, leaving time for questions and discussions. So David Alexander, we'll start with you, please.
Yeah, thanks, Jeff. So my name's David Alexander. I'm a professor in the Physics and Astronomy department here. I'm the solar physicist. I'm the non-medical person, I think, on the panel. I'm also the director of the Rice Space Institute. As I said yesterday, the kind of medical phrase I learned yesterday was we used the biggest hammer that we had. When it comes to radiation, one of the biggest hammers we have is the sun, and that's what I kind of study. So there's just a couple of points I wanted to make to kind of set up hopefully some of the other discussion. One of the things we're trying to do in solar physics, of course, there's two parts to it. There's the science itself, which is where we're trying to understand the sun as a star and how the sun interacts as a physical system with the Earth. But kind of the other side of that coin is the operational aspect and the environment in which many of you have worked and are trying to mitigate for future work, is understanding that space environment around. We have a thing called the Space Weather Prediction Center up in Colorado, and the idea is to try and predict some of these large radiation-producing events. Now, I don't want to get into a lot of detail, but remember that we have photon radiation, so that's X-rays and extreme ultraviolet, the ionizing radiation, and we also have particle radiation. Some of the biggest issues we worry about is the particle radiation, solar energetic particles, solar proton events, energetic solar particles. We somehow use the letters S, E, and P in all the combinations that we can, and they sort of mean slightly different things. One of the challenges, particularly for spaceflight and particularly for spaceflight into deep space, is it's one thing to predict an event, which we're not there yet anyway. It's one thing to be able to predict an event. It's another thing to be able to predict the characteristics of that event. If it doesn't help if you're constantly crying wolf that there was a solar flare or a coronal mass ejection when it's not coming anywhere near you if you're on the surface of Mars, on the way to Mars, or orbiting the moon. And so it's important for us not only to be able to predict when an event may occur, but also what the characteristics of the energetic release of that event. What is the EUV and X-ray emission? What does that look like? What energies are we talking about? What does the particle spectrum look like? What are the fluencies of those particles? How long do we expect it to last? And there's challenges between what we see in the sun and in the case of a flare. The light takes 8 minutes and 19 seconds to get to the Earth, a little bit longer to Mars. We have a little bit of time, but sometimes we don't know the important characteristics. In the case of the Earth, we don't know the important characteristics until it's about half an hour upstream from us, and that's just not enough time to react. So we have to be able to sort of find a way of predicting a lot of these things and be able to characterize those numbers as at different locations in the inner solar system. And so a lot of the focus, if you follow this at all, a lot of the focus has not so much been to predict that, but to at least be able to predict an all clear. So in other words, if you think you're going to be all clear for 24 hours, the astronauts can make their EVAs and all those different things. So that's a slightly simpler problem. It relies on a little bit less physics and more on the observations, but we're actually actively trying to get further. Where the sun comes in with respect to, I know NASA feels, I believe this is correct, my colleagues here can correct me if I'm wrong, but if you know there's an event coming, you might prevent or delay an EVA, but pretty much you can shield again. There's lots of particles coming from the sun, but the energies are sufficiently low enough that you probably can get away with reasonable amount of shielding and be confident that the dosages are going to be fairly low. When it comes to the galactic cosmic rays, of course, and you also know where that radiation is coming from, it's the sun. But when it's galactic cosmic rays, they're coming from everywhere and can be 100,000 times more energetic. And so that's a real problem. Where the sun comes in is what we do know is that the sun, with its 11-year cycle, modulates the ability of galactic cosmic rays to get into the inner solar system. And so one other prediction tool that we're still struggling with, but there's some progress being made, is to be the ability to predict at least the characteristics of the solar cycle. You might know you might not be able to tell when a specific event is going to happen, a flare, a coronal mass ejection, but you at least should be able to plot out the how many sunspots there's going to be and how that's going to vary over the 11-year cycle. That becomes important as you're thinking of multi-year missions, both in the planning, in the launching, in the transport time, and the time on the surface of Mars. And so these are things that I think we can make progress in. We have this thing called the Heliophysics System Observatory. Heliophysics is a word that NASA made up, and it's taken me about 10 years to actually like it, but now I kind of like it. And that includes everything from the Voyager spacecraft to the recently launched Parker Solar Probe. So we're getting very close into about 3 million miles from the sun. And of course, the Voyager spacecraft are, we think, at least in and out of the solar system itself. So we have a huge number of systems. We have detectors on Mars Curiosity and so on as we try and learn about this radiation. So to finish, just a couple of things, because we're not going to touch on that here, but I just wanted to make sure, and most of you are aware of this, and it kind of came up in the last session too. We also have to develop the ability to sense this radiation. And ideally, with machine learning and some of the technology developments, I hate to mention artificial intelligence because we all get worried about that, but with machine learning capabilities, we might be able to develop sensors that are sensitive enough, with a background knowledge that's strong enough that we can maybe have an early warning system. In other words, if you're walking around the surface of Mars, if we had the right kind of sensors, we might be able to give those astronauts enough warning to get back into the habitat. And Nick Stoffel is sitting up at the back. We were just talking over lunch. He's been working on some really interesting sensors from his days as a student at UH and now at Johnson. So I'd encourage you to talk to him and look at the stuff that he's doing. And there's some developments going on there. And then the last thing I'll mention, well, actually, I'm going to mention a science fiction thing, but before I do that, the last thing I'll mention is the idea of mitigating this. And I think there's a lot of materials research, advanced materials research, being carried out at universities around the country, and particularly developing, it's actually for fuel cells and for efficient energy systems. And so the idea to infuse materials with as much hydrogen as you can is turning out to be very important for hydrogen-based fuel cells, but that also turns out to be really good for radiation-resistant materials because hydrogen, as we know, is a very great absorber of this radiation. So that kind of technology is being developed and needs to be integrated in, because if we know how much we can mitigate then we can actually start thinking about the kind of biological impacts that we need to consider. The science fiction thing I want to mention, it's not quite science fiction, but one of the things that we focus on is the effects of radiation on people, obviously for very obvious reasons, is the Space Medicine Summit. But what we also have to consider is the effect of radiation on the bacteria that makes humans function. And when you have bacterial systems, and I'm getting out of my depth here when it comes to the science, but the mutation rate goes way up when you're under ionization radiation. And so while the astronaut might not be affected for another 20, 30, 40 years, what happens to that bacterial system that the astronaut relies on is as it's mutating very, very quickly. If you're on Mars, if you're Elon Musk, for example, and you've got a colony on Mars for 20, 30 years, you might have to worry about this. So how does a human adapt to that adapting microbiome, for example? And so that's something, and it just maybe the circles I go in, but I don't hear that talked an awful lot about. It's not the highest priority, but it is something as we go deeper into space and longer, it's something that we might have to consider. So those are kind of my little thoughts on the whole process here. Thank you.
Yeah, no, thanks very much, David, for those remarks. John, do you want to introduce yourself?
Sure. I'm John Charles. After a career of almost 33 years as a NASA civil servant, I retired about a year and a half ago. I'm still emeritus with Judy Hayes, although she would deny that she sees me very often. I also see by the program that my affiliation is Space Center Houston, which makes me not the first person ever to be present at this conference associated with a museum, but possibly only the third, so I think that's a bit of a distinction. And an additional affiliation I have in my retirement is I'm a consultant to a company called STEMRAD, which makes radiation protective garments. More about that in a second. As the chief scientist of the Human Research Program for the best 6 years of my NASA career, I had to know everything about everything in space life sciences, and darn it, I almost made it except for the radiation part. When I retired, I was still deficient in that. But now I get to pretend like I know something, or at least get to bask in the aura of people that do know things about space radiation. And I wanted to say a few words about one of the couple of components that are listed as topics for our discussion, that is shielding for protection and for countermeasures. Now, Dave just described to you the space radiation environment, and not knowing anything about physics, I just think about what do you do to avoid something bad. If we all agree that radiation is bad, then you probably would like to minimize your exposure to it. And one way is to dodge it if you can, and Dave talked a little bit about the prediction capabilities that we might be developing. I don't think you can actually dodge around photons, but you might be able to go when there are no photons, no energetic photons or electrons present. You can also try to outrun them, and that's not very successful, but you can try to spend less time. If you can go fast, if you have a super duper warp drive, you can travel quickly between your source and your destination and try to minimize the exposure. And failing all of those, as you will with our current technologies, you just have to try to minimize the detrimental effects, and you do that with shielding. You can shield your entire spacecraft if you have a magnetic field strong enough to make a mini Van Allen belt around you, or with a magnetic field, and then shielding from the radiation effects. And if you don't happen to have a fusion reactor handy, then you can probably do it with physical shielding, with mass shielding. I think that's called parasitic shielding. I'm not a specialist, though. I think that's the word to use. And you can shield the entire spacecraft, or you can get more and more particular and just shield the living compartment, perhaps the sleeping compartment. And if you're really anxious to minimize the mass that you carry as shielding, you just shield the person. You provide the person with protective garments. And you can either shield the entire person with a whole body radiation suit, or you can shield the most radiation sensitive organs. And now I'm talking about the work that the company I consult for, called STEMRAD, has been doing in terms of radiation protection for radiation workers, first responders, people that respond to radiation environments on the Earth, and branching out into radiation protection of astronauts' most radio-sensitive organs, mostly in the thorax, the sensitive tissues of the lungs and the breasts and the blood-forming cells and so forth, with a product that is called AstroRad. AstroRad is a set of shielding garments that provide selective shielding through variable thickness, a shielding algorithm which complements the body's self-shielding capabilities. And this internal shielding is provided by components that consist of thousands, I got to read this because it's really cool, thousands of tessellated hexagonal shielding parts made of polyethylene of some sort, which behave in a scale-like manner to maximize the flexibility and the freedom of movement and the comfort of the shielding garment. So it's possible to shield yourself with a vest of water if that's your style choice, or you can go with lead if you happen to have a lot of excess propulsive capability to carry mass in flight. But there are ways to provide maximize the shielding in the areas where it really needs to be shielded. So this is a technology I think is one component of a healthy future space flight. And but don't take my word for it. You will be able to judge for yourself. The first of the possible garments, it's a vest, will be launched on the next resupply mission to the space station, which is called nowadays NG-12. Will be launched on November 2nd out of Wallops Island for some ergonomic testing aboard the International Space Station. So be sure to look for the female crew members that are wearing the Star Trek-like dark tunic during their normal daily activities. And also, just for your information, this is a bit of an update, I think, from the last time I talked to you about this. The first Orion spacecraft to depart Earth, officially this time next year, probably earlier in the following year, will carry 2 radiation-sensitive mannequins on board, provided by the German Space Agency. One of those 2 mannequins will be wearing a vest of this nature provided by the Israeli Space Agency. It's an Israeli company, providing the opportunity for actual direct side-by-side comparison in the real world or real outer space environment of the radiation protection afforded by garments like this. So this is an example of extremely localized shielding that may be, as I say, part of your healthy space flight going forward into the future if you're unable to provide adequate radiation protection from the other capabilities that I mentioned, addressing the risks that Dave addressed. So this is an interesting possibility, and I think there's probably more capabilities like this to be developed by developers from around the world that can minimize reduce or minimize the risks of radiation on the human body. Thank you.
Yeah, no, thanks a lot, John. It's very interesting. So, Kristen Faber, this is your first ISMS meeting, so welcome.
This is, and I am fairly new to this area. I started last December at Trish. So I'm Kristen Faber. I am an assistant professor at Baylor College of Medicine in the Pathology and Immunology department, but I'm also a part of the Center for Space Medicine. And I have the joy of being the senior scientist at the Translational Research Institute for Space Health, or TRISH. And so I'm really liking what I'm hearing so far. I mean, Star Trek area spacesuits coming in, that's really exciting. And David, what you had mentioned about science fiction, I really like what you said there, because how Trish thinks is really our mission. Our partnership with HRP is to think about how are we getting to Mars. So we have to think 20 years from now. And so we kind of live in that science fiction to science fact realm. So how do we really push the technology? How do we push our imagination? How do we push our research to get us that paradigm shift or that disruptive technology to get us to Mars? So it's really a fun and exciting job to have. And with in terms of radiation, we got to think about this in a little bit of a different way. And so we've had decades of really interesting and exciting work. We understand a lot about cellular mechanisms, DNA repair, non-targeted effects. We've done a lot of understanding with physics. So how can we converge a lot of the novel technologies and new perspectives and new ideas and new approaches to solve the radiation problem for space exploration? And things that we could be interested in are how do we monitor that? And so you were talking about sensors earlier. And so how about biosensors? How can we personalize the type of damage that we would get on a space exploration? So can we have biodosimetry? And if we can do that, would we understand if the galactic space radiation that we would be facing, is that really going to be a significant problem? And if it is going to be a significant problem, what tissues are going to be susceptible? Is it going to be anything that has the stem cell population, anything that has cellular proliferation? Do we need to be focusing on other tissues? So we think about that a lot. We also think about countermeasures. And so, of course, there are a lot of countermeasures that are out there that are pharmaceutical, nutraceutical, but we also think about other approaches for countermeasures. And so there could be materials, there could be shielding. Dorit mentioned earlier about some of the research in our portfolio about looking at gene editing. And so we have a couple of projects that are using simple models, simple animal models, to understand what genes will sensitize tissue or sensitize cells to DNA repair in the presence of radiation. But then conversely, there are genes that if they were modified or upregulated could protect from radiation. So can we understand and translate what we understand from simple in vivo models to human cells and to human tissues? So that's one area that we can explore for countermeasures. We can also try to understand how we can test countermeasures in more of a humanized model. And so moving on or adding to a lot of the in vivo work and simple in vitro studies that have been done in the past, let's start adding human complexity to that. And so, for example, we have a project from Chris Parada who has a humanized mouse. And so what do I mean by a humanized mouse? And so they're actually able to have these mice that have the hemopoietic or the bone marrow tissue of the mouse is about 75% human cells that are produced in there. So not entirely a human tissue within a mouse, but you can start to add some human questions to an in vivo model to start to think about, well, how would human cells, how would human tissue respond in the presence of radiation? So that's another area that we're also looking into. We're also really interested in these novel technologies. Again, it's a convergence of different disciplines, and so engineering and biology, so bioengineering to create these complex human in vitro models. And so these tissue chips or organs on chips or microphysiological systems, essentially what that is a screenshot, a microenvironment of a tissue of interest in your body. And so it's this human tissue engineered to replicate what those tissues would experience in the body. And therefore, we can really control that microenvironment, those multicellular 3D scaffold complex environment to understand what's happening to that human tissue in the presence of radiation. And so if you think about all of the different tissues that we could potentially be interested in, like the cardiovascular system or the blood-brain barrier or the bone marrow or the gut, can we start to use these types of technologies to understand what happens to human tissue in a physiologically relevant environment to predict what will happen to the person, but then also really focus on how do we approach the countermeasure effort? How can we personalize this? And so if we can engineer these models so that we're using these inducible pluripotent stem cells. And so if I take somebody's cells and then convert them into a stem cell-like tissue, and then I can direct those into a cardiac, or maybe I want to have vasculature tissue from that person, and I can understand how you will respond to radiation, and can we actually have a countermeasure program for you, so something that would be more effective for you, because we are starting to understand that not everybody will respond to radiation in the same way, and they probably won't all respond to a countermeasure in the same way. So these are things that we're thinking about. And as a matter of fact, we are actually having a solicitation coming out in the beginning of January to try to address just that. We actually are going to put a solicitation out for looking at complex human tissue engineered to study space radiation and countermeasures. So we really are trying to drive our efforts toward that next phase, that next generation of radiation research. So if you have any questions with that, you certainly come to me.
Thanks, Kristen. Peter?
Yep, thank you very much. So my name is Peter Norsk, and I'm working as an element scientist in the Human Research Program. And since nobody knows what an element scientist is, I can define it as the lead scientist for an element of a program. And an element is a department. So I am responsible for the research within human physiology and the development of human protective measures against the negative effects of the spaceflight environment, in particular weightlessness. So my background is not at all in radiation. I know actually very little about radiation. So why am I in the radiation element? And that is because the program is now pushing for much more integration between disciplines, not only within our program, but also with other programs. And radiation is one of our key collaborators, understanding the combined effects of all of the spaceflight environmental factors on human physiology. So the combined effects in particular, weightlessness. I say weightlessness and not microgravity because it's one of my old key themes that microgravity is not the correct expression. It's weightlessness and combined with radiation and isolation as well. This means that we are working closely with space biology for understanding fundamental mechanisms of the effect of radiation and weightlessness, and in combination. I'm working very closely with Dr. Tom Williams, who's actually present at this meeting. He's the lead scientist for the human factors and behavioral science and performance element, and he's in charge of understanding effects, also of the combinatorial effects of spaceflight environmental factors, and in particular the central nervous system. So we work together, and finding that integrated approach is one of the challenges I have every day, and I enjoy it very much because I learn a lot every day about not only space radiation, but about a lot of aspects of science. What are we in human physiology concerned about when it comes to the future missions? Is there anything, as Dr. Pelosky, our director, will ask, anything that keeps you up at night? There are actually a lot of things, but also something concerned with space. And one is, in fact, on the combinatorial effects of adding deep space radiation that we actually know very little about because we cannot exactly reproduce it on the ground on Earth. Combining that with weightlessness is of concern. If you look into certain biomarkers at the cellular level, and you look into an organism like mice or rats, and you hind them, suspend them to unload them in the lower body for simulation of weightlessness, then you may not see an effect of a particular biomarker. If you then separately irradiate them with as close as possible to deep space radiation level, you may not see an effect. If you do both, you sometimes see a huge effect. So we are concerned about exactly that. Are we at the cellular level doing something fundamentally by combining those two unique environmental influences? Are we doing something that could lead to a health decrement that is of concern for mission performance and success? That is what keeps me up at night, if something should keep me up. And that's why we are doing research from the cellular level up to the integrated level. We are, at the cellular level, we use bioreactors. That's what in Europe is called the slow rotating clinostat for simulating of weightlessness on the cells. Combining it with radiation and looking into fundamental processes, we support that. We have seen actually synergistic effects on increased permeability in cell cultures of the cerebrovasculature, which is of concern for, among all, SANS, space flight associated neuroocular syndrome, and brain function. So that is of concern. At the integrated human physiology level, we are supporting rat studies at the moment where we're on the ground, hind them, suspending them, and combining it with radiation to look into cardiovascular inflammatory effects. This is still being worked out by a group between two groups. One is Dr. Delp and the other one is Dr. Baker. We are looking into, we are doing animal studies on ISS in mice, and we have 2 different studies looking into basic fundamental effects on ISS, which then later will be compared to hopefully research being done in deep space and Gateway. And then we are very much pushing for and involved in the coming 1-year missions, when particularly we're looking into all kind of physiology, but the cardiovascular physiology is of particular importance, and that was kind of establish a control in low Earth orbit for later deep space mission research, measuring the same variables in astronauts and hopefully also animals. So the one big next step for us and for the program is to understand by longer duration flights with 1-year missions, the basic effects of weightlessness and isolation, and then compare it to what we see in deep space and Gateway, and during the missions that will then be more and more extended, and hopefully end up with a 1-year deep space mission before we go to Mars. And that is what keeps us up at night. We do see effects in animal models, but will we see effects in humans that is of a health concern? We don't know yet.
Okay, thanks a lot, Peter. Becky?
So, hi, I'm Becky Blue. I'm also a casualty of integration. I am not a physicist. I am not a radiation expert. I am a physician. And like most of the physicians in this room, when I first started trying to learn about radiation, it sounded big and scary and terrifying. And I really didn't understand anything about it, except that it has, to this point in my career, seemed like a showstopper when we start doing things like mission risk planning. So 2 years ago, I was assigned to start reaching out to as many radiation people that would answer my request to talk to me and to teach me and to try and start understanding that. And that's what I've been doing. So since then, I have had a slightly better grasp. Those that work the most often with me, which are mostly the Shrag folks, may think differently, but I think I'm starting to get it. At least I think I'm starting to be able to talk a little bit better about it. So let me kind of talk you through the way that this problem is phrased in my mind, because I think it helps to have that context when you start looking at it from a medical point of view. What do we need to worry about it, and how should we worry about it, right? So the very first thing that I was asked to do when sitting down with the radiation folks is characterize this acute risk. When we start talking about various design reference missions, when we start talking about planning for the future, first, acute. Do we need to be worried about acute radiation exposure during flight based on what we currently know? So here's how I approached it. I said, give me the worst day in recorded human history, okay? And for this purpose, I used the 1974 massive radiation solar particle event that we know about, right? The 1972 event exposed or would have exposed astronauts to rather large radiation doses to blood-forming organs. We also said, give us the worst vehicle we can even imagine designing. So for reference, consider an unpacked Apollo vehicle. Therefore, an Apollo vehicle where the hull is all you get. There's nothing else inside. An unpacked Apollo vehicle has a shielding capability of 6.15 grams per centimeter squared. We said, make it worse. Let's look at a 5 grams per centimeter squared. Worst day we can think of, worst vehicle we can think of. What is the dose? The dose to blood-forming organs in that circumstance is 0.46 gray. 0.46 gray translates to a 2% incidence of nausea, very unlikely vomiting, a 17% incidence of weakness and fatigue, and a performance nadir. If you take a scale of 0 to 1, where 1 is normal, perfect astronaut performance, a performance nadir expectation of a low point of 0.8, 80% performance capability. That is the worst day scenario in recorded history, and certainly it could be worse, but worst day scenario that we know of. Worst shielding capacity that I could think of, okay? If we raise that to 10 grams per centimeter squared of shielding, okay, that would drop the blood-forming organ dose to 0.26 gray. If we raised it to 20 grams per centimeter squared, that would drop the blood-forming organ dose to 0.08 gray. At 0.08 gray, the likelihood of clinical sequelae, based on what we currently know, is exceptionally low, if not minuscule, okay? So from what we currently know, and I keep saying that because that's an important point, and I'm going to come back to that in a second, but based on what we currently know, based on our current translation of risk, that makes me think that acute radiation exposures are not an in-mission risk driver for spaceflight based on our current design reference missions. We know we're going to have better shields than 5 grams per centimeter squared, and I know that based on the current worst-case scenario we could think of, it's probably not going to be all that bad. Does that mean there's no risk? No. But we're going to come back to that. So let's pause and talk about long-duration health risk, right? Long-duration health risks, there's a lot of them. Dr. Norsk just mentioned, he's working on all this integrative concern for CNS, and cardiovascular is another risk. But right now, the way we plan for mission risk for long-duration health impacts is by looking at cancer. Not looking at whether you're going to get cancer, but looking at whether you're going to die from cancer. And there's some problems in that, but we're going to start with that because that's where we start from, okay? And we allow a 3% increase in the absolute risk of death from cancer because of radiation, right? That is what we have established as our exposure limits, right? So if we start there, we have, I say we as if I have any ownership in it, I do not, but the radiation folks have spent a lot of time recently improving upon how they calculate that risk. And I would be happy to do my very, very best to do a bad job of walking you through that calculation. But the bottom line is they're really good at it, right? And they already take that model and incorporate a lot of conservatism. They don't want to be wrong. So with all that conservatism built in, they are able to calculate out the risk of you dying from cancer because of X amount of time spent in space. And if you look at the numbers that they're able to pop out of that model based on the current updates and the massive work that's been done in the last few years to improve upon these calculations and incorporate all the new data that are coming in from all of the sources that we pull in, all of our survival data, what we know is that 3% absolute risk increase limit that we've set for ourselves only gets exceeded for a 3-year planetary mission to Mars. Short of that, we're within limits. So what am I saying? What I'm saying is, based on what we currently know, based on our current best model calculations, and they're not guesses, right? They're pretty good. Based on those current model, the risk of radiation-induced acute radiation clinical sequela or radiation-induced death from cancer are not mission risk drivers for most of our scenarios short of a planetary Mars surface mission. Does that mean there's no problem? Nope. Absolutely not. And as you've heard the last 4 people say, there's a lot of things we need to keep working on. I've mentioned that we need that 20 gram per centimeter squared shielding capacity. We could do that in a lot of ways. Dr. Charles presented one of those ways that they're looking at to try and meet that. We know we need to meet that, but they're working on how to do that better. We know that there are additive consequences from all the various risks of spaceflight that go into making radiation a little bit different or a little bit confusing based on what we know. One of the major problems that we have is a very poor translation and interpretation of what we know to what we don't know. We know that exposures in spaceflight are just different from the entirety of the human experience here on Earth. The vast majority of what we use to do these calculations comes from sources such as atomic bomb survivors. Those doses and dose rates and types of exposures are just different from what our astronauts receive in space. We need better translation of dose rate, type, and complexity of exposure type. Most of our analogs use a single type of exposure. In space, you get a fairly complex mix of different particles, right? So we need those types of studies to give us some better information about whether or not we are jumping to the right conclusions. We need populations to provide us better insight. Most of our research, as I've mentioned, is based upon the idea of atomic bomb survivors. The million-person study is going to try and help that out. So those are new data that are coming out on populations that are a little better matched to what we may consider pertinent to our astronaut population. Those data may help improve these models. We need use of non-human models that maybe bear slightly more similarity to humans than rodents. They're awfully cute, but they're not little humans, right? So we need some of these translational models to improve upon our understanding, and the other members of this panel have great ideas. I don't. I'm not a physicist. This is not what I do. All I'm trying to do is wrap the medical brain around what it means and what we need to plan for. And the short answer is, based on our current understanding, let's go. But when we go, let's make sure we track all of those data to make us smarter for the next trip. I think that's all I want to say.
Yeah, thanks
Go
a
on,
lot,
Jeff.
Becky. Really appreciate your perspectives, and you may not be a physicist, but you're surrounded by them. And one is to your right, so Jeff.
Can I just say ditto? And stop there? No. So, hi, I'm Jeff Chancellor. I think most of you know me from all of my excellent presentations over the years on this panel. And entertain a lot of you with my comments, I think. So I'm a nuclear physicist. I do mostly computational physics and some experimental work. I've been working in space radiation either for or with NASA for 20 years now. And I just moved my lab to LSU, where I'm a professor in the physics and astronomy department. So last year I was told that what I said resonated with a lot of people, and I don't remember at all what I said because I was overtaxed. I didn't prepare, and I just came up here and started talking. So I'm going to see if I can strike lightning twice today. I didn't prepare. So what I want to do is go through and just make some comments on what everybody said, because I thought there were some cool things made, and I can maybe provide some perspective on my history at NASA, where I was a flight controller working on the radiation console. I was also in the mission management team for like 4 space shuttle missions. I did the shielding analysis and design for Constellation. I did program management, and now I'm doing fundamental research. So I have a weird perspective on all this. So I think David is probably the most important person on this panel right now, because the solar particle event risk is what's going to kill the crew, and it's going to end the mission. Full stop. So the work that they're doing right there to be able to predict it, because we can't, and we haven't been able to in 60 years now. That's why they call it nowcasting. Basically, we see it coming, we know it's coming, and we react. But let me provide perspective on how we react. So he mentioned that light gets here in about 8.5 minutes. So some of these solar particle events were so energetic that in October of 2003, there was an event that happened, and it got to low Earth orbit in 14 minutes. These things were smoking fast. So let me tell you what happens as a flight controller at 2 a.m. when the Space Weather Prediction Center calls you at home. You answer the phone on the 3rd time because it finally wakes you up. They tell you 3 times what's going on, because it takes 3 times for you to wake up and understand what's going on. By the time you get up, back then I had a whole lot more hair, so you smush your hair down because you know you're going to be on NASA TV, because you got to go talk to the flight director. You get dressed, you make sure you don't have your clothes tucked in your underwear, you don't look like an idiot. You drive down to Mission Control, badge in, go to the flight director, convince him you're supposed to be there, convince him you know what you're talking about, convince him he shouldn't call security and have you thrown out, and convince him that the crew is a threat. You're talking probably an hour or 2 that the crew has been in a high dose rate environment. So that speaks not only the need for being able to predict it and see it coming, but also for developing technologies where the crew can be autonomous. Not only will they be warned of a high dose event or a high radiation threat, but they can assess it by having the material to look at the spectrum and the energies, and perhaps do on-board real-time assessment of what they need to do to take precautions. In most events, I've seen it take 3, 4, 5 hours for the crew to react to an event, just because of all those circumstances and uncertainty. I did do some work with the Texas Center for Superconductivity and Material Science on hydrogen-rich materials, and what we showed is most of the time, and that was 15, 20 years ago also, it only reduced the dose from a solar particle event, maybe 3 or 4%. So I don't know, and haven't seen any advances since then, so I don't know if that's a solution.
Boron nitride, you can do 20%.
Okay, I didn't know that. It's good to know. Okay, I'll have to look into
I
that.
don't know the dose calculation, but
Okay.
they're getting really
Right.
high fusion.
Okay, cool. I didn't know that. The body shield, cool idea. Doesn't sound very comfortable, but I don't want to go to space anyway, so I wouldn't want to wear it. I think it's a great idea for solar particle events, and it will enhance any shielding. In Constellation, we didn't meet the requirements for shielding. The idea is we would take parasitic polyethylene and deploy a storm shelter during the event of a solar particle event. So this would be more of a mobile storm shelter. It won't do anything for the galactic cosmic ray threat. They're going to bulldoze and blast through that without even hiccuping. So it doesn't really provide much there. With Kristen, I agree on 100% on everything you said. Radiation is done wrong. And I've been saying that for years now. As you probably mostly know, we approach it as a terrestrial radiation health program, and it's not. It's completely different, the type of radiation, the dynamics of the radiation, how it interacts on the fundamental, nucleon level is completely different than terrestrial radiation. I agree 100% on integrating the radiation element throughout the human research program. Absolutely, I think you should dissolve it and it should be part of all the other programs. Radiation is the multidisciplinary curriculum or research project. And when you have biologists pretend to be physicists and physicists pretend to be biologists and everybody pretending to be a physiologist or a physician, you just get mayhem. And you get what you have right now. No results, 0 results on the questions being asked from radiation are now, today, are the same, are what they were asked during Gemini, Mercury, Apollo, the space shuttle. No progress at all. The Apollo vehicle shielding, yeah, it's 5 grams. I always want to make sure people understand it's the only vehicle on the most powerful rocket ever built to take humans outside of low Earth orbit. So you should assume that's the shielding we're going to have on every vehicle we take into orbit. Although it didn't kill the crew on that large solar particle event that happened in August of 1972, that dose inside the vehicle did cause the crew to exceed their 30-day and 1-year limit on the blood forming organ dose. So we have this risk posture for space radiation because there's never been a clinical diagnosis attributed to space radiation. So everything's done on risk assessment. So with that in mind, this means that a crew in space would exceed these limits and they would immediately be brought back home or grounded, or you have to take other precautions for them to continue healthy. The 20 grams of shielding, see my comments on Constellation. It's a lot. I don't know if we'll meet it with the basic launch capabilities that we have right now. And then finally, I was going to address some of these topics, but I think I did, because when you're talking about shielding protection, you either have to talk about solar particle events or GCR. You can't talk about them both the same, but you can have twice the shielding of what we have on the space station, which is about 50 centimeters of mass, and that's a lot in space. You can double that, and you want to attenuate the galactic cosmic ray radiation threat even a little bit. So it's not even an issue with that. Until we understand what the nature of the risk is, we really don't even need to be talking about how we're going to shield it because we don't know what the risk is. I would question whether or not we even understand what dose means in radiation at this point. And then the one thing I do want to talk about on the comments is the effects of long-term radiation on brain performance. I've talked to a lot of people who do clinical radiotherapy. They don't see this in the clinic from 15, 20 gray for people being treated for cancer. If you look at the experiments that are being done, I think they're very elegant and well done and nice, but they always come to a conclusion that are very over-inflammatory. So I'll ask this. How many cosmonauts and astronauts in the audience have flown for 5 or 6 months or more in space? Cool, I see 3. How many of you are babbling idiots? Outside of, because all of y'all have exceeded those thresholds that these studies have shown that you're going to have severe cognitive impairments. 100 gray is what they're talking about in a mouse model. So it's probably likely more like 50 centigrade, not 100 gray, 100 centigrade, excuse me, in a human model. And a lot of it has to do with the biological and the environmental model are so flawed that you can't even really say it represents the space radiation environment and a human in the environment itself. I would argue that the way we do it, the radiation analog is maybe 0.1% representative of the environment. And the last time I checked, again, I say it every year, a mouse or a rat is not an astronaut in most cases. So I'll end it there and take questions.
Okay, we have time for a few questions.
Those two, yeah.
Yeah. Sure. Kevin? Do you? No, no.
Thank you. I've got 2, if you'll let me. First is, I do love the analysis of the thin-skinned Apollo vehicle on the worst SP event in history. But given that we've been told now that your forecasting ability may be down to minutes, surely the worst vehicle you can be in is an EVA suit. I'm sure that's less than 5 grams, right? So what do those figures look like for that?
Sure. So there's a really great paper that was written in 2008 by a person named Xiaowen Hu that I can give you after this if you would like to see it. And he does calculate out those doses, and they're scary. You're right. So an EVA suit, based on old EVA suits, we average those to about 0.3 grams per centimeter squared, as opposed to, like I said, an unpacked crappy vehicle being 5, right? All things considered, it's a bad day. But here's the thing. When you're out on EVA, and those folks in the audience who have actually done EVAs, by all means, please correct me when I get some of the details wrong here, but everybody wears a personal dosimeter. And at the same time, folks in the SRAG group, the Space Radiation Analytics Group, sit in the back room and at all times monitor sun activity and monitor for things like this, okay, especially during EVA. They're not at home asleep. They're in the back room actively monitoring with a finger on the button to talk to the flight director, okay? If a solar particle event occurs, right? Because 2 years ago, that was also my terror. Oh my God, what if they're outside the vehicle? But here's the thing, and Jeff's going to tell me where I'm wrong here in a minute, but if it happens, your dosimeter is going to go off. A heck of a lot of alarms are going to go off in that room down on the ground, and people are going to start calling up saying, go inside right now. And the thing about SPE is that they happen over hours to days. And yes, they get to you fast. And yes, any exposure is not a good exposure. But anytime you can get behind a shield, you get behind a shield. And so if we can get inside in a matter of minutes, and during an EVA, somebody's watching at all times, not coming from home, they're watching at all times. And if it happens and your dosimeter starts pinging and those alarms start going off and we say, go inside, you go inside. And then you're behind your shielding. Does that make sense?
I think I'd also, maybe you can correct me too, Becky, is that when it looks like there's a very active sunspot, which is where more flares come, CMEs are a little bit different, but typically it can be associated with large flares. If that is a very complex and dynamically evolving sunspot, then I think they basically postpone the EVA so that they don't have to even go through that particular protocol. So there's a little bit of warning there. And yes, everybody's watching all the time. The sun's not just up during the day. And so there are some things in there. But I think you are right about the space. The other thing I would caution about, and I think this touches on what Jeff said too, there's a danger of increasing the shielding too much, particularly for galactic cosmic rays, because the secondaries become really important. And you can actually generate low energy neutrons, and they're hard to stop. And so I don't know enough to know. David Warden, I don't think, is here. So there's an issue when you add more shielding because you think that it's better, you've actually get more targets for the radiation to interact with and generate secondaries. And then that can make its way into the capsule, and the dose can go up by adding more shielding.
And the biggest problem with that in particular is that it's crazy complex. The intravehicular environment, if you pass GCR, which is already complex, through a shielded compartment, which scatters and makes it more complex and more alterations of those energies, we're really, really bad at modeling that. So when it comes to all of these ground-based research analogs that we've tried to do to try and figure this problem out, that's one of these pieces that we're really, really, really bad at. We cannot currently, based on current experiments that have been published and are available, we have not successfully modeled those intravehicular complex crazy doses and dose rates that we just don't do on the ground. So we have very little understanding of it.
So I'd like to add to that, Becky, and you're right that there is a potential if you're out EVA to get into shielding, but what we modeled during Constellation for lunar surface ops was a situation where the crew was out on EVA at least an hour from their HAB. Okay, and this could be in a covered rover that was partially shielded, or it could be an open rover like we had during Apollo. In that particular case, with an hour back in one of the worst case scenarios that David brought out, which is 8 minutes to X-ray and then another 5 minutes where we've seen particles coming in, it's a bad fluence and flux type of situation, then the crew could get to prodromal effects during that time period, which would be a 0.125 kind of REM sort of scenario. So that was the worst case that we modeled during Constellation. You remember this, Jeff. So and I agreed. So that's unlikely to have dramatic long-term mission effects, but it could have some potential mission impact during that particular EVA. I think the thing for Kristen that's important is to understand is what sensors are you going to put on those mannequins? Because you remember all our ISS dose measurement has been in low Earth orbit, so it's been in a protected environment. So we need to know, especially something that's going to go outside of LEO, and you're going to have shield on one and no shield on the other. What are you going to measure? Because David is very right in the sense that the neutrons are the key to all of this, and some of them are not low energy, some of them are moderate energy, and they have much higher biological impact. 10 to 20, quality factor compared to the incident radiation. So that's what we need to know to answer those questions.
Right, and I agree. I think that the sensors for a neutron, especially in the craft, is going to be a big consideration or a big issue that we would have to deal with respect to exposure. For the sensors that I'm talking about, I'm actually thinking about like actual biosensors. And so like some of the biomarkers that the individual would produce within the body to have like their own personalized dosimeter. And so I would envision, and we are just starting to explore this space. And so right now, of course, like there's a lot that can be done with cytokine expression. You have the DNA damage. You can do like circulating micronuclei. And you can look at chromosomal aberrations, but we want to certainly expand past that, and that's hopefully what we want to try to get at with this upcoming solicitation. Is in the presence of neutron radiation, for example, what kind of readouts do these human-based tissues release, and can we actually start to translate that over to what would happen in the person as they start to go on these deep space missions? And so we are just now starting to explore that, but this is absolutely, I think, critical for us to understand for us when we move forward on these deep space missions.
Yeah, thanks, Kristen. So very sorry. I know folks have more questions, but we've reached the end of this session. So I want to thank the panelists very much for their excellent perspectives.